to welcome everyone to the Whiteman Lecture for 2015. This is one of the highlights of the academic year here at Monmouth College. The Wendell Whiteman Memorial Lecture annually brings a noted business executive or scholar to our campus. This lecture series began in 1992 and is named in memory of Wendell Whiteman, a Monmouth College alumnus, a distinguished alumnus of the college, a member of the class of 1927. Mr. Whiteman worked for 50 years at the Monmouth Security, Savings and Loan, including a 24-year tenure as the association's president. Following Mr. Whiteman's passing in 1992, his family established this lecture series in his memory. It was established by Wendell's three sons, Don Whiteman, member of the class of 49, Ralph Whiteman, member of the class of 52, and a member of the Board of Trustees, and Dick Whiteman, class of 64, and Ralph and Dick are with us today, so if you guys would, please stand and let us thank you. We're also pleased to have another distinguished alumnus of the college in attendance today. Logan and I had the pleasure of meeting Karen Loya at an alumni event in Washington back in November. Karen is a member of the class of, maybe I'll let you tell your class year. I always get in trouble when I tell class year results. But this suffices to say that Karen is a distinguished alumnus of the college. An outstanding scientist in her own right. We are really fortunate to have two such individuals with us today. After graduating from the college, Karen received her doctorate at the University of Maryland, College Park, and went into a distinguished career in research, began working for IBM. I think early in her career, ended up working for quite a while as a lead scientist and project manager at the Goddard Space Flight Center based in Greenbelt, Maryland. And again, Logan and I had the pleasure of meeting Karen at this event in Washington and immediately said, we would love to have you come back to campus as soon and as often as possible to speak with our students, not only as an example to our students in the sciences, but as an example particularly to our young women for careers in science, technology, engineering, and mathematics. One of the great things that Logan and I both discovered early on and that we very much treasure about the college is its history of empowering women from the very beginning. And we're glad to have another example of that in Karen here today. So, without further ado, let me turn this over to Emily Bell. And Emily is a member of the class of 15, a senior about to graduate, although we won't remind her of that. Logan and I have our youngest son is about to graduate from college as well. And just found out today that he actually has a job. Yeah, exactly. Yeehaw. But Emily has been one of our outstanding students. Emily is also a distinguished scientist. She's going to be continuing her studies in graduate school at Colorado State University, where she's going to be working on radioactive reflection, the use of radioactive reflection for the detection of carbon in the atmosphere. Obviously a very important topic for all of us to be considering, and the effects of that indeed. She was part of our first class of Midwest Scholars, and she's held leadership positions in several campus organizations, including Alpha Xi Delta, Rotaract, and the Disney Club, in addition to being a Scots ambassador. Please welcome Emily Bell, class of 15, who will introduce our distinguished speaker today.
Thank you. I'm thrilled and honored to announce this year's Whiteman Lecturer, Dr. John C. Mather. In your programs, you can read about Dr. Mather's career, which includes currently serving as Senior Astrophysicist and Senior Project Scientist for the James Webb Space Telescope at NASA's Goddard Space Flight Center. And you can read about his education, which includes receiving his PhD in physics from the University of California, Berkeley. I was drawn to some additional information about Dr. Mather that you won't find in your programs. For example, there are many scientists and teachers in his family, including his parents, and he also grew up in what he likes to call a peaceful farming community, much like one that described Monmouth. A book called Astronomy Made Simple sparked his interest in space, and the rest is history, or the history of the universe, to be more precise. It was Dr. Mather's work It was Dr. Mather's work as project scientist for NASA's Cosmic Background Explorer, or COBE satellite, that earned him the 2006 Nobel Prize in Physics, which he shared with George Smoot. Their work essentially confirmed the Big Bang theory of the origin of the universe, which is a phrase about Dr. Mather that's printed in all of the posters around campus and in all of the marquees downtown. And perhaps the shortest, sweetest introduction of Dr. Mather can be provided by Stephen Hawking, the noted theoretical physicist. Hawking called the COBE team's work the most important scientific discovery of the century, if not of all time. Ladies and gentlemen, please welcome the man whose work led to arguably the world's most important scientific discovery, this year's Whiteman lecturer, Dr. John C. Mather.
Thank you for that lovely introduction. Is this microphone still turned on, or shall I switch to the other one? I like to roam around. Anyway, I'm just so pleased to be here. This is because of Karen, and my friend and colleague on the COBE satellite project, because she mentioned one day would I come out, and I said yes. So I'm really tickled to find out who's here, and who the faculty and the students are like, and to meet Emily, to meet the Whiteman brothers, and hear about their family and their contribution to the college. So, as was mentioned, I grew up on a farm, and this is it. This is a little farm in northwestern New Jersey, about a mile off the Appalachian Trail, which people don't appreciate. Most people that haven't been to New Jersey much think that it's 5 miles wide inside of a turnpike. So this is where I lived. That barn housed 20 bulls, and those bulls were the fathers of tens of thousands of cows that they didn't ever eat. This was a scientific laboratory as well, where Geiger counters and nitrogen and all kinds of things in those barns there. So I grew up, I think my first interest in science was piqued when my dad told me at age 6 at bedtime one night that people are made out of cells, and the cells have chromosomes, and those chromosomes determine our heredity. And when you're 6 years old, that's pretty mysterious. So by the time I was 8, we'd seen the Museum of Natural History in New York, and the displays of the dinosaur bones, and the volcanoes, and a planetarium show. And gosh, wouldn't that be exciting to know more about it? So that got me started. So I've been trying to be a scientist ever since, but in those days I didn't know what it was. Even though my dad was a scientist, we were here on this farm because that was his profession, to study the genetics of dairy cows. And by the way, he was there partly because he wanted to make an improvement in the world. He grew up in southern Africa for a few years, his first 9 years, and he noticed that the cows were all skinny and didn't give much milk. And so he thought, well, this could be improved. So he went into research for dairy cows. A little contextual information here. One of the reasons this is important for a lot of us is actually written by our first almost scientist president. Before he was president, this was in the Declaration of Independence. He wrote about the laws of nature and of nature's God, and then he wrote, or we wrote, our ancestors wrote, we hold these truths to be self-evident, that all men are created equal, they are endowed by their Creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. So imagine that you're a scientist and you want to say, how do we go from the laws of nature, maybe the Big Bang that we know about now, to people that can write those words. That's a big jump, and I don't know how we did it. So I will say that we scientists are working on the easy part, telling you what the atoms do. The historians and the philosophers and the psychologists will have to tell you how we got to being able to write those words. Anyway, so a few beautiful pictures that we've gotten from the Hubble, just to give a little perspective. This is a picture called the Hubble Ultra Deep Field. So they decided to point the Hubble telescope at this place in the sky, which as far as people knew, was pretty nearly empty. Nothing to look at. And people said, you're going to waste your time if you're going to do that. And what they found out was instead of being empty, it had these thousands and thousands of galaxies in that picture. There's one star in that picture over on the right-hand side, and the rest of them are all galaxies. So what's a galaxy? It's like the one that we live in, the Milky Way, and it has about 100 billion stars orbiting around a common center held together by gravity. So, okay, so that was out there, and the reason we did expect this was we thought galaxies had all been formed very recently. What we found from the Hubble picture was that they were formed a very long time ago when the universe was very young, and it wasn't that a surprise. So this was one of the biggest shocks that first came out of the Hubble Space Telescope. Here is a closer by one of those. This is called the Whirlpool Nebula for obvious reasons. Nebula means a cloud in Latin, but for a long time people didn't know that it was made out of stars. So that particular cloud is made out of 100 billion stars, and you see there being orbiting around a common center. We think that's like the Milky Way that we live in ourselves, except we live inside it and you can't see it from outside. So anyway, we have to figure this out by looking at the neighbors that imagine what we ourselves look like. Here's another interesting picture from the Hubble. This is a star that blew up in AD 1054, and it was observed worldwide because you could see it in the daytime. We actually know what day it happened because it was written down, and some records still survive from the Chinese astronomers. And it's nowadays called the Crab Nebula because it looked like a crab to some early astronomers. Now we know that it's this amazing expanding blob of stuff that's the debris from the star that blew up. And so maybe this isn't too much of a surprise. You look in the mirror in the morning, you are looking at exploded stars because every single one of those atoms that you are made of was somewhere else. And the Big Bang did not give us carbon, oxygen, nitrogen, iron, sulfur, and all the rest of the things that your body is made of. Gave us nitrogen and helium. So when you're looking in there in the mirror, you're not just doing cosmetology, you're doing cosmology. Imagine this amazing idea that atoms are made of were born in stars that blew up. They probably blew all the way out of our galaxy, traveled hundreds of millions of light years, fell back in, recycled generations later. In fact, that's probably our history. So I'll show you a little bit about how astronomers come to these kinds of conclusions. So number one, we look back in time. We look at things as they were when they sent light out. So light travels really fast, but it's not so fast that it doesn't matter. You can see things as they were. So if you see the sun, you see it as it was 500 seconds ago, the nearest other star as it was 4 years ago, the middle of our own galaxy as it was about 25,000 years ago, and this chart is old, so when I wrote it, I thought the universe is about 15 billion years old. We now know it's 13.8 billion years old, measured. This was before we had a good measurement. So, how do you know how far back you're looking in time? Well, you use the known speed of light, and you survey. You measure triangles. So in your high school class, you learned about geometry, and you learned about triangles, and how you know the whole shape of a triangle if you know one side and two angles of the triangle. So that's surveying. It's a little more complicated than that. But the ancient Greeks would have known how to do this. In fact, they did know how to do this. They measured the distance, the size of the Earth, they got it about right. They measured the distance to the moon, they got it about right by these methods. They would have understood perfectly well the other method that we use called the standard candle method. If I have two objects and I say that they're identical and they're shining, and call them candles, and I see and I look at them and one of them is a lot fainter than the other, I say it's just because it's farther away. And it's called the inverse square law. So this now enables us to survey the entire universe with geometry and the inverse square law to tell how far away stuff is, and therefore how far we're looking back in time. Next thing we want to know is, well, how is stuff moving? Stuff moves, the sun moves, the earth moves, the moon moves. It's a little matter of perspective, but didn't really move. But when things are far away, you can't see them move. But you can measure one thing about it, done with a technique of spreading out the starlight into a rainbow, into a spectrum. And so in the upper left picture there, we see that we spread out the light of, say, the sun, and we see there are little dark bars across the rainbow up there. It's because there are atoms and molecules in the atmosphere of the sun, and they absorb and stop certain wavelengths of light from coming to us. So now if I look at another star and I see, well, it's got the same shape of spectrum, the same brightness, same lines in it, I say, well, it's a star a lot like the sun. I have just done immediate chemical analysis of that other star. And they're not exactly all the same. In fact, they vary quite a lot. But the other thing I can do is I can see, well, what if all the wavelengths are multiplied by some number? And we'll say, well, that's because it's moving. So you can hear this with your own ears when you're out on the highway. If a motorcycle comes up behind you, and then pitch of the engine suddenly drops as it goes by. So that's called the Doppler shift. It's been known since, I think, 1850 or something. So it's almost the same in mathematics as in light as in sound, except we don't put in relativity. So anyway, now we can measure the motions of distant things. So back in 1929, Edwin Hubble drew this chart, and we discovered the expanding universe. So people now call it the Big Bang, which is an improper name, because we actually believe the expanding universe, and expanding pretty darn fast. So his units are incorrect according to modern tradition, but the main point was that each of these dots on here is a galaxy, and what he's plotted is the speed of motion, almost all of them are going away, versus the distance. So you see there's a trend line there, and if you divide the speed into the distance, you figure out how long it took everything to get there. So that's the age of the universe. Divide the distance by the speed. First time we do it. Now, Hubble got it wrong, because his candles that he was comparing were not really identical. So he thought the age of the universe was about 2 billion years, and it's actually 13.8. So there was a mistake, and it took us another 50 years to find it. But at any rate, this was a shock. This was front page news around the world. This is the same year that the worldwide economy collapsed. So remember, if you want to know when the Big Bang was discovered, that was it. So it had been predicted, by the way, by George Lemaitre. Here's his picture coming up. That's some other folks. Here's Mr. Einstein in the middle. He gave us relativity in 1905. He gave us general relativity, which he used for cosmology, in 1915. So 100 years ago, we got the equations we needed to have to work on this question. 1915. 1922, Mr. Friedman there, working in the Soviet Union in Leningrad, figured out that Einstein's equations implied the universe must be expanding. 3 years later, he died. It was a bad time to live there. In 1927, George Lemaitre did the same calculation again. He said, I think the universe started with a primeval atom. That was his word. And Einstein said, well, that couldn't be right. Everyone, isn't obvious that the universe must be static. And Einstein had already put in a constant into his equations to make sure the universe could be static, to balance the attraction and gravity of everything for everything else with a kind of repulsive force, kind of anti-gravity. So Einstein had that in his equations, and that was what he later described as his greatest blunder. Because he could have, should have, according to modern perspective, understood that his equations implied the universe must be expanding. But there was no evidence for that. In fact, in 1915, when he was working on those equations, we didn't even know galaxies were made of stars, not really. It was just barely beginning to be understood. So maybe we should excuse him for that. But he was wrong about it. He said to Lemaitre, your mathematics is correct, your physics is abominable. So he wasn't polite either. Curiously enough, his constant did come back. Anyway, some other folks on the picture, George Gamow in 1948 was a Ukrainian physicist working at George Washington University in D.C. And he had 2 young colleagues, Robert Herman and Ralph Alford there, shown in the lower left corner. Now, Alford wrote a thesis under Mr. Gamow and worked on the idea of the Big Bang, which we now could calculate. We learned about neutrons and nuclear reactions during the World War. So now we should calculate the universe. And 300 people, that's like this whole auditorium full, came to watch his thesis defense, because this was revolutionary work. That was about the atoms that would be created in the Big Bang. Then later on, he and Herman wrote a paper that said, it was hot there. The heat of the universe should still be here. Where is it? It's got to be here. It's got to be everywhere. And their paper predicted the temperature of that heat, 5 degrees above absolute zero, which is pretty darn close. It's 2.7. So they only had slide rules for computers in those days. That's pretty remarkably good and close agreement for that purpose. So, however, nobody went to measure. If they had known that there was a Nobel Prize waiting for them, they might have tried. Nobody tried. So, anyway, it took a while for that subject to get rolling. So, I'm skipping the other stories here. Hubble's law, by the way, tells us that there doesn't have to be a center of the universe. Now, when people say Big Bang to you, do you not picture a little firecracker? It's a little bang. It's not nearly big enough. What we should say is infinite bad. The infinite universe expanded infinitely into its infinite self. So maybe that gives you a different picture. Anyway, one of the consequences of it is there's not a center and there's not an edge that we can find. It's not that we didn't look. We did look. And no evidence has ever been found that there's a center. Except it feels like we're in the middle. But of course, it's been a long time since we realized we weren't really in the middle of anything. So anyway, there's probably not a center. So my three astronomers can all compare notes, and they can say, well, I think I'm in the middle. There's no grass in outer space. Nobody knows who's moving and who's not. So there they are. They all concluded their race started an hour ago. They all think they're in the middle. So it also means I don't have to draw you a picture. I cannot stand outside the universe to draw you a picture of the universe. And so if anybody draws you a picture, it's wrong. There's no way to draw a picture. You cannot imagine, and the pictures that you do show and see in artists' drawings in the magazines, they're all wrong because they imply, and to your mind, the incorrect idea that it happened at a place. What it actually means is it happened everywhere at the same time, so the universe is expanding into itself. So don't ask me afterwards, where was it? It was there, it was there, it was there, it was everywhere. It does not have a middle that we can find. I'm not saying there isn't any middle, but we can't find it. So then you might say, well, that's a lovely story, but my Earth that I know about doesn't look like it's expanding. So how did we get here from there? So here's our short version. Gravity, reaching across very large amounts of space, is able to stop the expansion of the material and pull it back and make it collapse back into stars and galaxies. So the upshot of that is, well, the early universe had to be a little bit non-uniform. There had to be places that had enough gravity to stop from expanding, and that would sort of serve as centers for attraction. So that has to be true if gravity is going to work. And then after it does work, of course, the stars can make the atoms that we're made of, and the Earth can exist as formed from recycled material, and it can all get going. So that's how that's supposed to work. So we have a capsule story of the whole history of the early universe here on one page. We start with a picture of the early universe. I said it was not possible to draw you a proper picture, but we can still make a map. We can make you a map of what the sky looks like. And so there it is. That's a map we made with the COBE satellite. And that's the one that Stephen Hawking liked. We imagined that galaxies formed by small things coming together under gravity to make big ones. There's a nearest big galaxy nearby. That's the Andromeda Nebula in the lower left corner. And by the way, it's coming at us. I heard a few giggles about the horrendous space debris. That's the name given by Calvin to Hobbes in the cartoon strip. It's a better name because it does not suggest that it was a little firecracker in the corner. So anyway, whatever it was that got us all started, the sort of short version of it is that nuclear reactions were over after 3 minutes. They got helium nuclei and hydrogen, and that was it. The universe became transparent when it was 389,000 years old because the electrons latched onto the atomic nuclei, and the light waves were able to travel without unlinking anything ever since. So they came to our receivers, and we can make a map of the universe as it was when it became suddenly transparent. So that's what that little oval is in the upper left corner. How the universe looked when it was young. As seen from here, as not seen from outside the universe, as seen from here. So then something happened. The stars were born. We've never seen that happen. We have some ideas about it, and then things move on. So, okay, so maybe that's true. So I'd like to show a little bit about Earth science because it's not my subject, but it's fascinating, and it's where the dinosaurs came from and all that. So. The solar system was born when the universe is already 9 billion years old almost. So we've only been here a third of the age of the solar system, of the universe. So we know this age by measuring the radioactive decay products in little grains of material that we find, and we look for the oldest ones. So we've measured that darn age really precisely. We think that the moon was formed by some giant cosmic quack. An object about the size of Mars crashed into the Earth about maybe 90 billion years after the solar system was born and made one heck of a wreck. thankfully we were not completely dried out at that time. Then later on, we got bombarded from above, and possibly that's where we got the water. So I'll show you a totally astonishing movie about the early solar system in a moment. Anyway, when the rocks stopped falling on the Earth, about 3.8 billion years ago, we also saw signs of life, fossil signs of life, almost immediately after the rocks stopped falling. So this suggests that maybe life is easy to get started, although almost all of us grew up thinking it must require a miracle. Nevertheless, whatever it was happened quickly here. So I guess for those of us that are interested in is there life elsewhere in the solar system or outside, this is the evidence that it might be. It might not be impossible, we just don't know how it works. So here's the movie that's a little astonishing about the early solar system. These are the planets orbiting around the sun. Those are the 4 big circles there. And then the little green things are comets orbiting around in the outer solar system. They're debris left over from the formation of the solar system. And people think the solar system is like a clock, it runs forever. The astrologers will tell you so. Anyway, it doesn't. Look in a moment. So that's just gravity doing that. It's a simulated movie. We can do this in the computer. We all agree that this is the right way to calculate it. So what happened? So almost all the comets were ejected. They went somewhere. And they went flung out of the solar system, maybe they hit the Earth. Maybe that's when we got the water that makes up the oceans. So this is an important factor about whether the Earth is the only place that could have life. Because maybe we need that ocean. Maybe we need that just exact amount of water. And maybe this is special. So this tells us whether it's hard or easy to find life in other solar systems. We might be rare. That's the conclusion of this kind of movie. We might be a very rare occurrence in the universe. Not unique, but rare. So, okay, now I want to talk a few minutes about the COBE satellite that Emily mentioned. This is the Cosmic Background Explorer. It was conceived a few months after I finished graduate school. And it was based on the idea that I told my thesis, my postdoctoral advisor, I said, my thesis project failed, but it should have been done in outer space. So he said, we'll call up our friends and we'll write a proposal. And it was a short proposal that said, our idea is good. We should go measure the early universe. And we're pretty smart young people. And we didn't know how to do this job. But a couple of years later, NASA said, yeah, it's a good idea. We will start studying this. We will assign a team of professional engineers at NASA Goddard Space Flight Center to work with you to figure out how to do this. And that worked pretty well. Then we were building it up, and it was going to launch on a space shuttle. In 1986, the Space Shuttle Challenger was lost. Had to redesign it. The engineers redid it, and it went up and looked like this. So it took 15 years from concept to launch. And within weeks, we were able to make our first scientific result. This one is a graph that confirms the expanding universe story. What the measurement is how bright is the cosmos in each of these different frequencies, how many waves per centimeter there are, that's in the horizontal direction, and the vertical direction, how bright it is. There's a smooth curve there, and that's called the black body function, and it's a simple prediction of how bright that radiation must be. And you see all the data fall right on the line. So when we got that chart up in front of the astronomers a few weeks after launch, they gave me this standing ovation. And I thought, doesn't everybody know that's the right answer? But no, we didn't. So that was my first taste of fame. I had no idea how important this was going to be to people. The next one is the one that Emily mentioned that Stephen Hawking liked so much. Here's that map again. The map in the lower right corner is a map of the hot and cold spots of the early universe, and they actually correspond to density differences as well. So it means the early universe had the density variations necessary for gravity to cause us to exist. So most of those hot and cold spots are made by dark matter. Astronomers know that it's there, nobody else can see it. We can't see it either, but it makes gravity. So because those spots are there, Stephen Hawking is happy because we can now study stuff, we can learn about the early universe even better, but we also know that we're here because of those spots, and we didn't know that before that. So it turned out we got the right answer, and it was measured much better by another NASA satellite a few years later, the microwave anisotropy probe. And this map agrees with the first one, it just has much more detail. And so that led to, in 2006, a phone call from Stockholm saying, are you the right John Mather we're talking to? We want to give you a prize, and these are their words. For the discovery of the black body form. And that black body form is that smooth curve that I showed you with the little boxes on it. It means that the Big Bang or the expanded universe story is roughly correct. And the anisotropy. Anisotropy means, and it's not iso, the same entropy direction. The universe has bumps on it. So those two discoveries basically changed cosmology from pure speculation into detailed measurement, and we've been doing it better and better ever since. So I got to go to Stockholm. I showed my chart a lot. I still like to show it. I got my diploma from the King of Sweden, there he is. And so did George, also another member of our team. So anyway, that proceeded. By the way, just a slight diversion from the science story, there's a check that comes with the prize. We put it into a little foundation, which goes to science students, engineering students at NASA Goddard, and also to ballet students. My wife is a ballet teacher, so interests and recognition that these things are all partnerships. That's the way that one is going. By the way, George and I received the prize, but there's a little book about the work that says 1,500 people worked on the project. This is a team project, and that's sort of the secret that everybody knows, that big projects take teams. And they happen not because one person is brilliant, but because many people are brilliant, and they're pulled together by the idea. The idea that you can measure the early universe, in this case. So by the way, that was the second Nobel Prize for that radiation. The first prize was given for the discovery back in 1965. Now I want to show you the work that led to the third prize in the Nobel Prize in Cosmology. We've been expecting the universe to slow down because gravity was pulling everything together. And so for many decades, people thought we would measure that. So this is the diagram illustrating that the galaxies slow down because they're pulling each other together. In 1998, however, it was discovered that the opposite is true. They are going faster and faster. Expansion is accelerating. And so we now call the reason for this the dark energy. And that is a completely useless name. It says we don't know what it is. But curiously enough, it turns out that constant that Einstein put in his equations fits the measurements perfectly. So he was right, then he was wrong, he was right, or something. Anyway, so these are the three guys who shared the Nobel Prize in 2011 for that discovery, for finding out that we were wrong. And by the way, a lot of people think science is about how much we know. This is about how much we don't know, and how important it is to find out and work on the stuff that we don't know. So when you study in your school that how to do this and how to do that, that's preparation. Eventually you have to work on the stuff nobody knows. So now I want to talk about the new telescope that I'm working on, which is called the James Webb Space Telescope, and what we're doing about that, and I'll wrap up with some stuff about the future of our world. So we know from the Hubble Space Telescope that we haven't seen everything. Hubble is great, but it doesn't see what we can't see either. It does not see infrared. So infrared light is heat radiation. We can sense it. We can feel it with our skin. Rattlesnake can sense it, but it shows us a different universe. That's how some people look when you take an infrared picture. So astronomers said after the Hubble was launched, well, what are we going to do next? And they said, build us one of these telescopes. So here it is. It's called the James Webb Space Telescope. James Webb is not the current day politician, but actually was the second administrator of NASA. He's the guy who went up to John Kennedy and said, this is what it takes to go to the moon. And by the way, then it was enough. So that was his version of informal risk analysis. He was right. He was betting the future of the country on getting this right. Can you imagine what we would have done and felt if we had gotten halfway done with the project and said, it's messed up? He would have been blamed, and it would have been considered to be a management fiasco, and we would have not demonstrated that we were better than the Soviet Union or anything. So it was brilliant. Anyway, so here we are, and we're honoring, this is the first time we're honoring an administrator instead of an astronomer by naming a telescope for him. So the telescope is constructed by a large team. We're leading it from NASA Goddard Space Flight Center just outside Washington, D.C. So I'm the head scientist for it, but there's a huge team for this project as well. There are about 1,000 people currently working on it full-time. So it's an international partnership with Europe and Canada. They've done most of their parts in Europe and Canada, except they're buying the rocket, which hasn't been bought yet. They will do that too. Anyway, so the telescope is there. You see that it doesn't look like anybody else's telescope. It looks more like a solar energy concentrator out in the desert. And so it is sort of like that. But we will come back to that. It will be launched in 2018 from French Guiana by the European rocket. And let's see, it's cold. The telescope is protected by that big blue thing. That thing that you see there is actually we call it a sun shield. It's about as big as a tennis court. So imagine Roger Federer running back and forth over half of it. And so this is a big deal. That mirror, that hexagon, is 21 feet across. So you could get it more or less into this center section here, but I don't think it would quite fit in our auditorium. So it's huge, and it is bigger than the rocket. So I will show you a scary movie about how we unfolded in space. Here are some more detailed pictures of it. You see how it's folded up in the upper right corner to fit the top of the rocket, and how it's unfolded in the left to see how it's being in space. Here's our scary movie. This is what it takes to unfold it after it's launched. The rocket is fully packed with this material. First thing that we have to do is unfold the solar panels to get electricity, and then the little parabolic dish to send the information back and forth to Earth. Now we're unfolding the sun shield, the umbrella. This takes place right away after launch within the first couple of weeks. And you say, isn't that pretty damn complicated? Yeah. Isn't that kind of scary? Yeah. What you're going to do to make sure it works? Practice. Well, and also have two of everything where you can. That's really essential, because there's some things you just can't make it out of. And number two, have a lot of smart people tell you when you're making a mistake. So if you ever are afraid of making a mistake, you know what you have to do? Get people to tell you when you do make a mistake. And so then you can fix it before you push the button and launch the observatory. So also, by the way, the only reason we can even get to do this is that this is not the most complicated thing people have put up in space anyway. This company that we hired is called Northrop Grumman, and they work for other government agencies to produce even more complicated stuff, which they can't tell us about. But because they do that, we astronomers can order a telescope. And if we send enough money, we will build it. So there it is. And it's finally unfolded enough, but it still is not ready to work because it's still warm and it's still not focused. Here's where we're sending the observatory. It's called a sun-Earth launch point. It's 1 million miles out from us. So start from the sun, go to the right, and see the Earth. Go past the moon 1 million miles, and there's the launch point L2. And we're going to orbit around that. This is where we go. It's a good place. Here are some of our mirrors that have been tested and cooled down in a big tank at Marshall Space Flight Center in Huntsville, Alabama. And they are the right shape. They're all done, by the way. They're all stored away in their little storage canisters at Goddard in Greenbelt, Maryland. A year ago, we put our instrument package together, and this is what it takes to do that. There are people in their bunny suits in their clean room. You cannot tell who is who. but the thing they've been working on is that carbon fiber structure with silver foil on it in the back. So that contains the cameras and spectrometers, take the instruments, take light from the sky and turn it into bits that can be sent back to Earth. So there it is, a little closer up. So it's all been tested out and it worked fine. So here it is being lifted into the test tank at Goddard. It's a huge, huge project. So when we started this off, I don't think anybody really appreciated how hard it was. And Congress very nearly killed it because nobody knew how hard it was. But they decided instead of killing it to give us the money that we said, and that was 4 years ago, and we have stayed on the plan ever since, which makes me very happy. So you might say, well, how are you going to focus this thing? Everybody knows the Hubble telescope was launched and it wasn't in focus. So we learned how to do that from the Hubble telescope. We learned how to focus after launch. So we built a test bed only this week so we can practice. So I told you practicing was important. Well, this is how we do that. Here is a movie of our clean room at Goddard. Here is testing an unfolding process. So this is going a whole lot faster than reality. So of course, how are you going to simulate zero gravity? Well, you have strings that pull things towards the ceiling, so that hold up the weight. Okay, so this particular piece of apparatus is just a test unit, a simulation, so we learn how to do stuff. After we put it together here at Goddard in Greenbelt, we put it on a truck, we drove it around Beltway, and sent it down to Texas for the next step. So this is how it goes to Texas. Put it in the truck barely fits under the bridges. When you get to Andrews Air Force Base, you drive the truck into the airplane, and then you fly to Texas and do it. In Texas, we have an even bigger vacuum tank. This is the same one the Apollo astronauts used to practice getting out of the capsule onto the surface of the moon. And so it's on the historic register. So anyway, we put the telescope in there. It's just the right size of tank for that purpose. And it's just really big enough. But it works. So this is what we have to do to get ready for launch. Now I want to show you what we hope to measure and observe when we get it launched. So here is a movie of the universe. This is what gravity does to those hot and cold spots of the early times. Our gravity pulls the material together. And so this is a simulation in a computer, and it's about the first time people think we might have the right answer in this movie. So this is a movie we cannot actually observe. We cannot wait for billions of years, and we cannot go back in time to see if this movie is really correct. So what we have to do is take this simulation of the early universe and say, well, what would a photograph of the sky look like if you could get a photograph that was based on that model? So we're about to find out. So this, by the way, shows that first gravity pulls stuff together and then stuff starts to explode. These reddish regions and explosions are stuff coming back out. I told you exploding stars make stuff go back out of the galaxy. That's what that's doing. So we're pretty dang recycled. Recycled stars, not just recycled dinosaur breath, recycled stars. It's gorgeous to watch. We don't yet know if this is really true, but it might be. So when they simulate this thing, it's like running a weather computer to simulate what's tomorrow going to be like. You start with what it is today and put in the laws of nature that you know about and see if it works. So maybe. Here the universe is almost 9 billion years old in this picture. That's when the solar system is being born. So this is about when the things quiet down. So maybe it's important that the solar system is not one of the originals. We don't know whether life could have survived for long in that early chaotic time. There is a possibility. And here's something, a coming tool. Let's see if this is going to work. Yeah. This is coming in our future. That beautiful Andromeda nebula that I showed you, it's heading straight for us. In a couple of billion years, it will be here, and this is going to happen. So what happens when two galaxies collide? The stars come right past each other, because they're far galaxies will combine, and this is probably going to happen. So if there's an astronomer here in a couple of billion years, it will be very exciting. I'll show you in a little bit that we have to do something. We probably have to move by then. So this is what happens when galaxies collide. And you say, well, you know that works well. Yes, we've actually seen many, many galaxies. Pictures out there will see the two galaxies in the process of merging together. So we know it should happen. We know it does happen from pictures. So that's what happens. Spectacular in our future. So other things we hope to see. Well, nature has given us extra lenses for our telescope. Gravity bends light. So in the upper right corner of this picture, you can see a very, very distant galaxy that's been magnified by the lenses in space by gravity bending light. So extra lenses for the telescope is really, really handy. We will see stuff, and actually we've got hundreds and hundreds of examples of this, able to see even farther. Here's one of our more pretty pictures from NASA. All this Field Nebula. This is a place where stars are being born as we speak. Have just been born, and darn if we can't see. The action is happening inside the dark regions. Dust clouds in space are blocking out a view of the exciting stuff. And so when I was a graduate student, people said, we know that gravity pulls stars together, and we still think that, but we still haven't seen it happen. So infrared light, which is longer waves than regular light, will go around the dust waves and we can see inside. So this is the same place seen with infrared from the ground. So we hope to see how stars are made. So we can see planets. We have seen a few planets from the ground with fancy telescopes using what's called adaptive optics to compensate for the shimmering atmosphere. And this one in the lower right picture is a planet we see with the Hubble Space Telescope. So what you see in the middle of that picture is a little dot, and there's an oval around it. Then there's a big ring of glowing dust, which is orbiting around that star. And then there, in a little inset, there's a picture of the planet. And it's taken several pictures of it now. They've seen it orbit around its star. So this is the first time since we discovered Neptune that we've been able to say, I think there's a planet right over there, and take a picture, and there it is. So we can take pictures of planets if they're big and bright. We have another method also, which is the one that the Kepler Observatory is pushing very hard. If you wait long enough, this will happen. A planet will go in front of a star. And that's if everything's lined up right. And so the Kepler Observatory has been watching well over 100,000 stars to wait for this to happen, and they have observed about 3,000 or 4,000 cases where a planet goes in front of a star. And so we know there are a lot of them out there. Once in a while, the planet will go behind the star, and if you notice that, the total brightness will diminish for a little while. So we have this wonderful technique to find planets in abundance. It's really relatively easy, although you have to build drilling equipment to do it. So for those who wonder, are we patient enough to do this? The people who figured that out had to try 5 times before they got approved to build that observatory. Anyway, for us, the wonderful thing is some of the starlight goes through the atmosphere of the planet. So we can do the atmospheric constituents, look for water, other things in those planets out there to see how much like Earth they really are. And that would be a big step. So we'll do this. What are we going to do for an encore after that? So the Hubble, here's the Hubble telescope, and then the Webb telescope, and then we probably need to go a bigger one. So how are we going to do that? Well, don't know yet. We only know that that's what it takes to observe those little planets around other stars. So NASA's working on this. We're just beginning. This is so hard, we don't know how. We've got to figure out a way. The other thing we could do is one of these. The other way you can see a planet orbiting a nearby star is to put up something to cast a shadow of the star so that you can see it. Our problem is that the Earth is 10 billion times bigger than the Sun, as seen from a distance. So how are you going to do this? So the plan here is to put out a big blocker that will cast a shadow of the star on the telescope. So that's what we're about to illustrate for you here. This might be easier. So what you have to do is put the blocker in front of the star, but 50,000 miles away. Line it up just so. If you do that, then you should be able to see those little planets orbiting around that star. So that's something we want to try too. So just to wrap up, what are we going to do next? What is coming in our future? Well, I don't know. And if I did say I knew, you shouldn't believe me, because I honestly don't know what people are going to do. But we can tell that we're using that coal and oil pretty fast, and sometimes we're going to use it a lot, and then things will change a lot. By then, some of the coal and oil will turn into carbon dioxide, and it will change the weather and the ocean, and we'll see. I do not know what people are going to do about that, so I'm not going to worry. Maybe some of us here will be good at dealing with that, and it's going to be an issue for our children and their children. About 1 billion years in the future, we do know this though, the sun is continuing to get very slowly but very definitely brighter. And it's not because we measured it, it's because we know what its cousins are like. We can see that other stars out there that are like the sun do actually get bigger and brighter over time. So in about 1 billion years, it'll be too hot for us to live here, and we might want to move to Mars. So those astronomers that are going to be watching the collision of Andromeda Nebula with us, they should be out there at Mars. So I don't know if they're going to figure that out, but they better. So in about 5 billion years, the sun will swell up towards the size of the Earth's orbit. And that's called a red giant star. And then it's pretty tough for us to live here. Then in about 7.6 billion years, it gets tired of that and it shrinks down to be the size of Earth, a white dwarf star. And anyway, everything will change then. If there was robotic life that has been produced, it could live anywhere. But we'll see. Eventually, the universe will continue to expand and the sky will go dark. So people tell me this is a terrible story. So, however, it's what the evidence is suggesting. I do not know this is true, just what the evidence is telling us now. For instance, we do not know if the universe has a reset button. We don't know why it's accelerating. It could possibly decide on its own that it's tired of that and it's going to do something different. Or it could be that there are other universes out there and they're trying. So on the other hand, we can say, what are we going to do about it? And one thing you can pretty clearly see is that everybody's working on robots. In the high-tech business, there are robotic tractors. My niece's husband's working on those. There are robotic everything, so we've got robots exploring the planets already. They're digging holes in the bottom of the ocean to get oil. Whatever it is that we want to do, we've got assistance from the robot. So people are going to go traveling. I think we will get to Mars, but we're pretty fragile. We like to breathe. We like protection from cosmic rays. So when you do get to Mars, by the way, if you're one of those Mars settlers, you've got to have a spacesuit on all the time, or you've got to be indoors. So you cannot just go like farming on Mars. Sorry, all those wonderful stories we read about in the science fiction, they weren't true. Not yet. So on the other hand, if robotic progress continues as rapidly as it seems to be going, then in some generations in the future, you'll be able to say, well, Mr. Robot, do you want to go to Mars? Will you take me with you? I don't know who's going to own it or what they're going to do. But I'm afraid, even so, that we're not in great danger of invasion from other space aliens, because space has changed large. So I don't think we're going to get invaded by others, nor are we going to easily get to other stars. So there's still room for imagination. So to conclude, there's a little book, and there's lots of websites, of course, these days. Everything's on a website. So you can find out more about these stories by looking at NASA websites, and even at the Nobel Prize, which they did quite a good job of publicizing and translating physics and science into things that the general public can enjoy. So thank you very much for coming to hear the story. I will welcome some questions for a little while, and then we'll have to go on to our next event. Thanks again. question. One of the best questions I remember from TV once was, why is there air? You might remember the answer. Blow out vesicles. Different categories of answer. So your question.
Okay, I was kind of curious about the James Webb Space Telescope. I know with Gaia you have to take into consideration the collision of particles onto the telescope. You have to do that at the drawing point 2, and what kind of particles are you seeing? The effects of them? I'm quite curious.
Okay, so the question is about basically busted dirt hitting the telescope. And we expect some. There is a lot of dust in interplanetary space just orbiting around the sun. There's not a concentration at that launch point because it's an unstable orbit. So we actually had to fire our jets to stay there. So dust will not accumulate, but it still will be attacked. So somewhere in the telescope, the sun shield will be a hole about a meter across at the end of the mission. So that's roughly what we're dealing with.
What about the lifetime of these jets?
The telescope will carry fuel to keep the telescope in place and keep it from tumbling over, and it'll last for 10 years according to the plan. So maybe longer, but that's our plan.
I have one more. The current mission objective for James Webb is roughly 4 years. What occurred? Do you expect to get more time out of it?
Oh, yeah, our requirement is 5 years of observation. Everything's been designed to prove, as well as you can, that it should work for 5 years. We're carrying fuel for 10 years. So, and I hope for many more. So, by the way, if you're an astronomy student, we're having a workshop next month for people to learn how to work the telescope.
This is
Anybody that wants to do that, let me know.
This is more a cosmology question. You've got the end and the beginning. And I was listening to on public radio an interview with Roger Penrose about the eons theory. Can you comment on that?
Okay, well, I'm not familiar really with this theory.
Well, it just everything gets recycled and starts again and everything.
Yeah, so it could be that was sort of what I was meaning when I was saying we don't know if the universe has a reset button. Because honestly, we don't know what governs the dark energy. And maybe it's Einstein's constant, and maybe it's something else. We don't know if it's a bug or a feature.
What kind of corrections did you have to make to change the theory for the age of the universe from 15 billion years down to 13.8?
Oh, well, the original number that I gave you was based on very old measurements of the expansion rate. And so all we had to do was to measure the expansion rate correctly. And that's been done, a lot of methods now agree. The other thing we had to do was discover the acceleration, which changed everything. Now we know from the geometry that, and all the measurements that age is 13.8. For a long time we had a big problem with stars. It looked like stars could be older than the universe. So we knew something had to be the matter with that picture. But now it's been resolved that stars are not older than the universe.
Back on slide 20, you said that the universe started expanding. Accelerating. How is that so?
The acceleration was discovered by studying the standard candles that I mentioned, which in our case are called supernovae, a star that blows up. There's a certain category of them that are almost identical to each other. So we don't honestly not understand how they work, but we use the fact that they're almost identical. So we say, now let's measure the distances away. And so they found some that were quite far away, and they were 20% bigger than they should have been. 20% is a big effect, at least by now it is. So we had to figure this out. So the interpretation was the distance is not what we thought. The connection between the distance and the speed was not what we thought. So Hubble's chart has a curvature to it. And so the upshot is that it must be accelerating now and it was decelerating before. So that's how it was first found. That was that, 5 different ways to measure. I agree.
We also have a microphone upstairs, just in case many of you up there have questions for Dr.
Oh, I saw up on the screen there about the
sun heating up as time passes. What effect does that have on global warming?
The effect on global warming so far is very slow. A billion years is really short, really long compared to even a million years, or even anyway. So far it's not known to be an effect. The sun is a little unstable. It has done things to us in recorded history. In AD 775, it had a giant set of flares, solar flares, which were enough to change the carbon-14 content of the atmospheres. And it was important. If a modern one happens like that, it could wreck the entire solar it could wreck the entire electric power grid if we don't do the right thing. So the sun has its little fluctuations, but nothing that we've identified can yet explain the global warming as caused by the sun. It's too slow. We could get a surprise, because that's the excitement of science. But so far, we're not finding anything out about the sun that makes us blame the sun.
I have a question. There's just recently they have landed a satellite on a comet. What have we learned from that landing a few months ago? Or is it too early to know?
I think it's too early to know much of what they found. I think the first thing is what a wonderful and brave experiment team that was to be able to even try that. The last I heard from them was the equipment was in danger because they flew part of the observatory close to the comet and they got confused by the brightness of the material coming out. So they survived that encounter, and I think they got to steer a little farther away. The part that's on the comet, they're still waiting for it to wake up. Apparently when it landed, it ended up so that the solar panels didn't get much sunlight. So it's hibernating until it warms up again, gets closer to the sun. We hope that it will tell us more.
I wanted to ask about the James Webb Space Telescope again. I got a lot of questions about that. So, do you think we'll be able to detect different types of molecules when the sun is, when planets are transiting? Like, you said we could detect like organic molecules, but will we be able to detect like what kind of signals will we get from these molecules? Will they be strong? Will they be weak?
Okay, well, the Webb telescope was not originally designed for this purpose, so it's just barely capable of doing the job, so it'll be hard to do. We calculate that if there's a sort of large version of Earth orbiting a smallish star, smaller than the sun, then we should have a chance to tell if it's got enough water to have an ocean. That would be a big accomplishment. What else? What else we'll find? We don't know. It could be that the Earth is very unusual. I kind of think it will be. I think the Earth is unusual even in the solar system. So I think it will be unusual in other planetary systems as well.
In response to a question about landing on the comet, is this a kind of a prelude to our attempts to be able to divert meteors from striking the Earth?
Well, it's not a direct prelude. It was actually a European project to go land on a comet, so it wasn't us. What it would take for us to divert a rock is actually a pretty big rocket engine. Probably the electric-powered rocket, which we know how to do it, but we've never built one big enough to move a big rock. So that's the current quest is to use that. One of the points of the asteroid encounter with the retrieval is to demonstrate the technology that you would need to get people to Mars. So the electric rocket is one of those. So we're learning. That asteroid business is pretty hard.
On the age of the universe, there was a plus or minus 0.11 billion years. How and why did we get that number, and how susceptible is that to change?
Okay, that number is gotten from a lot of different methods. We have like 4 or 5 different methods to measure the age. So when they get an error bar, it's partly from comparing the different methods, and also we know how sensitive the equipment is and how uncertain the measurements are from each piece of equipment. So there's a big mathematical process to calculate how big the error bar should be. So yes, it is subject to change. That number on that chart is a little old, and the Europeans built a mission called the Planck satellite, and they get a slightly different number. It's still sort of within the error bars of the old, so we weren't wrong, but we don't exactly agree either. So this is about what we expect. But still, to me, it's astonishing that we can get a 1% measurement of the age of the universe when I was a kid, this could have been 15% off. It could have been completely wrong.
Maybe one more question.
What advice do you have for young college students today who are interested in science? What's practical?
Oh, practical advice for science students, potential science students. Well, number one is it's really important. Everything that we see in our society that might need some attention over the next century has a big component of science and technology about it. Energy resources, pollution control, everything about the fact that there are 7 billion of us sharing the planet that demands science. Medical stuff demands science. So if you're a science student and it interests you, do not be discouraged by the fact that you do not know all the answers. Because the essence of science is being up against what we do not know. So although the public might think scientists know a lot, well, maybe we might even want you to think that. But the essence of what science is about is finding out what we don't know and working on that. So my picture of science is, well, imagine the New York Times crossword puzzle. You just imagine it going infinitely far in every direction. And we're still working on the little boxes in the middle that we can work on. And so there's so much more to learn about, and we're going to need to keep on working on it for the rest of time, because we're here, and we keep changing everything. So have courage, and know it's important.
I think the last question is going to come from the balcony.
Yeah, right here. What do you think the purpose of our life is?
Actually, missed the last word there. The purpose of our lives. That's easy questions. Well, some people say, well, we're needed because the plants need the carbon dioxide. I think there's probably a better answer, which would be whatever you think your purpose is, that's your purpose. If you're looking for something outside to tell you, that's kind of hard to find. But if you look inside your heart,